go. So just to be super clear about this, exam number 2 is happening this coming Tuesday, and we covered what we needed for exam number 2 last class. So this is the official beginning of what's going to be on exam number 3. Memory is going to be the new topic as we go into now different areas of cognition, continuing our look at cognitive psychology. But just to be clear, today's class, this chapter, will be on exam 3, not on exam 2. So we're going to start by our look at memory by taking a look at long-term memory. And specifically, we're going to just briefly recap some examples of extreme memory. And then we're going to introduce the idea of the modal model of memory. And just take a look at the idea that there are different types of memory. So just the way that there are different modalities in your senses, you have vision, you have hearing, you have touch. We have different modalities of memory, so we'll introduce the idea of that model by taking a look at short-term memory, working memory, and long-term memory. We're going to continue our theme of looking at how things are defined and bring up a common criticism of the definitions for the modal model of memory. And then we'll take a look at memory structure by looking at a couple of CogLabs, first one being the Suffix Effect, and then different types of long-term memory, explicit and implicit, and looking at that with the Implicit Learning CogLab. So that's on the agenda for today. So let's get started. So last time we took a look at imagery and imagery representation. And we mentioned that there was the bad and the good. So the bad was change blindness. This really indicates just how poor a lot of our representations are. I shouldn't say poor because there's a judgment there. They're great representations. They do exactly what they're meant to do. They're just not as detailed as we thought they were. So our representations, as revealed in change blindness, show that we don't really represent a lot of detail in our imagery representations. But then you get things like photographic memory and what we saw with Stephen Wiltshire, and we can see that in some individuals, their memory for images, their memory for image information almost seems limitless, almost seems boundless. So we saw that his memory, his imagery representation is very detailed, and it preserves a ton of detail. And we saw this with his drawing of New York after a 20-minute helicopter ride. And interestingly, this also shows you how long his memory lasts, because these panoramas, they're 12-foot, 16-foot panoramic pictures. They take a long time to do. This is usually like a 3 to 4 day ordeal. Well, not ordeal, he loves doing it. This is a 3 to 4 day task for Stephen. He will draw for 8 hours a day. Like, he will just go at it. But he's human. It takes some time. So it shows you that the details that he has, he has them for a long time. He doesn't seem to forget them. The memory doesn't start fading, across the photograph, indicating that he has this memory stored. Number one, a lot of detail stored. Number two, stored for a long time. So this brings us to our topic of memory. So memory, as defined, basically, is the process involved where you take information, you have access to information after the original information is no longer present. So you still have access to a representation of the information, however, the original information is not present. So it's basically what you have access to after perception is done. So perception is the representation that you have access to when the information is present. So when I'm looking out at this classroom, I can see what people are wearing. I can see how everybody bundled up for this snowfall here. And that is information that is still present. I can just take a look out when you guys are present and I can see what you're wearing. Later on though, if I'm going to tell somebody about my class, I have to remember because the information is not present. You will no longer be there, and I will have to draw on information that is not present using my memory processes. So that's memory in general. And then what they did early on in memory research is they came up with this idea of modal memory. And it was known as the modal model of memory, and that's a mouthful. But anyways, it was the idea that we have different types of memory. We have different ways of remembering things, just the same way that we have different ways of perceiving things, vision and audition and touch and taste. We have different ways of remembering things. So they identified these different modes of memory. So the first one is short-term memory. And short-term memory, I'll just read this off because we're going to be talking about definitions. It's the system involved in storing small amounts of information for a brief period of time. So that's the definition of short-term memory. The system that's involved in storing small amounts of information for a brief period of time. So this is something like this example is going to age very poorly in the next 5-6 years. But if you've ever had to remember a phone number, that's using your short-term memory. I'll give you a better one. Names at a party. If you ever get introduced to somebody at a party and you want to make sure that you don't forget their name, that's short-term memory. You want to make sure that you remember their name long enough. You might not think to remember it forever, but you want to make sure that you remember it long enough where if you run into them at the party, you can be like, hey, George, instead of, hey, Chief, doing that thing. So anyways, that's short-term memory. Working memory is another type of memory. And working memory is your limited capacity system for temporary storage, and this is the key one here, manipulation of information for complex tasks such as comprehension, learning, and reasoning. So people oftentimes get working memory and short-term memory confused, and some theories actually combine the two into the same mode of memory. But the key difference here is that working memory is used for manipulation of information. So this is where you keep things in your mind, you keep things consciously available so that you can access that information. So if you worked as a waiter or a waitress, and you took an order but you didn't have your notepad, and you're trying to remember who got the steak, medium rare, who wanted the baked potato, who ordered the salad, who didn't want vinaigrette on their salad, who wanted vinaigrette on the side, you would put that all into your working memory so that you can manipulate it, so that you can work with it, so that you can make decisions about how you're going to use that, that memory. If you're doing homework, oftentimes this comes up when you're learning a new skill. Homework becomes difficult when a lot of information goes into your working memory. So if you ever see somebody doing a procedure, and we'll talk about implicit and explicit memory later, but if you ever see somebody doing a very complicated procedure, so I just finished teaching statistics, and when my students do statistics, it's very difficult for them sometimes for certain statistical procedures. For me, super simple. Does that mean I'm any more intelligent than my students? No, it doesn't. But what it means is that I have found ways of offloading statistics from my working memory into other forms of memory while they're still trying to work on their work, they're still using their working memory. So they are overloading their working memory system where they can manipulate things, whereas for me, because I've been practiced on statistics, I've been able to offload that into other forms of memory. So it's specifically the system that you have for the manipulation, for the working of, for the thinking about information that you're currently using. And then the last one we have long-term memory, and that is the system for responsible for storing information for long periods of time. So if somebody ever asks you about your best Christmas ever, that's probably a memory that's stored in long-term memory. If you bring up something where you're like, oh, I remember when I was 6 years old, and I really wanted this one toy, and I thought it was sold out, but then, I ended up Christmas morning, there it was. That's your long-term memory. You're bringing something back from a long time ago, And it seems to be almost limited in its capacity to store information. So nobody, contrary to what students might think sometimes, whoops, when you're learning new information, you will not run out of information. You won't run out of space in your long-term memory. So those are the three definitions. The working memory failed me in counting right there. So those are the three definitions that we're looking at. And we're going to mention some of these problems with definitions. So we have these three definitions, and when I was going through them, nobody really seemed surprised. Nobody really seemed incredulous. Nobody was really kind of looking at them and going, I don't know if that really works. Because these seem to be completely reasonable. But you can play this type of game that they're playing with other forms of memory. So if I was a memory researcher, I might say to myself, you know what, here are three modes of memory, but I have additional modes. I have discovered additional modes of memory. I have discovered what I like to call blue memory. And blue memory, you shouldn't write this down, it's not real, but blue memory is basically memory for anything blue. It's your memory system that you have for remembering anything that's blue. And we can remember blue things, so why don't we have, maybe we have blue memory. So if you remember that animal is called a blue whale, then you are using your blue memory. And if you remember what a blue rose might look like, you're using your blue memory. And if you know what those characters are, you are using your blue memory. So the fact that you can remember blue things could possibly mean that you have a blue memory system, a system evolved for storing information specifically for blue things. And that's not my only contribution to memory research. I also thought maybe we have Spider-Man memory, which I like to call, and this is things for remembering Spider-Man related information. So remembering that Spider-Man originally was in a red and blue costume, remembering that Tobey Maguire was the first actor to play Spider-Man in a largely released movie. So Spider-Man memory, continuing on, Garfield was the second actor to play it. If you remembered that, you are accessing your Spider-Man memory. And I also love this little tidbit of information. Does anybody know who that is? That is Spider-Woman. Does anybody know why she was invented? Why she was created? Back in the late 70s, Spider-Man and the Hulk were extremely popular. The Hulk because of the TV show, Spider-Man was just incredibly popular. He's always been incredibly popular. And a rival company decided that they were going to release female versions of these characters. So they were going to release a She-Hulk show, and they were going to release a Spider-Woman show. And Marvel caught wind of this and released two comics, She-Hulk and Spider-Woman #1, so they could steal the copyright so that this other company couldn't steal the copyright. So Spider-Woman here actually has the real-life superpower of protecting Spider-Man's copyright from infringement and intellectual theft. All right, so that's why she was created. She's a great character, though. I'm actually decorating my lab today, and Spider-Woman #1 is going to go on the wall. All right, anyways. So those seem to be ridiculous versions of memory, because all I'm saying is that, well, you have a way of remembering certain things. You have a way of remembering Spider-Man information. So that must imply that that's a different type of memory. That's a certain type of memory. And that is an extreme example, or a ludicrous example, of the criticism that was leveled against these definitions of memory. Because these definitions of memory, if you look at them, they're not really great definitions, because they're really just descriptions of what it is that we're trying to remember. So for example, short-term memory. If you take a look at short-term memory, it's literally there in the title. It's short-term memory. So what is short-term memory? Well, short-term memory is where we remember things for brief periods of time. Why is it for brief periods of time? Well, it's because of short-term memory. Well, what is short-term memory again? Well, it's a system for brief periods of time. Why is it brief periods of time? Well, it's because of short-term memory. You can see it's a problem. It's circular. It makes about as much sense as blue memory or Spider-Man memory. And if you take a look at working memory, what is working memory for? Well, it's the system to manipulate information. Oh, what do you mean by manipulate information? Oh, I mean that you do work with it. So what system is that? Well, it's working memory. Well, what does working memory do? Well, it manipulates things. Well, what's manipulation? Well, it's working. Well, what's working? Well, working is working memory. Again, we have this circular definition that doesn't really give us any insight in terms of what it's doing. And then finally, long-term memory. Once again, it's a system that's responsible for what? For long periods of time. So again, it's very much like blue memory, spider memory. Long-term memory, what does it do? It remembers things for long periods of time. Why does it remember things for long periods of time? Well, because it's long-term. Well, what does it do? Well, it remembers things. It's another kind of circular definition. So this is the case with these types of definitions. And this is the reason why memory structure is vitally important. Because if you have different modes of memory, if they actually exist, if they're actually real things, then there has to be different structures underlying them. Because otherwise we're just playing the blue memory, spider memory game, where we're saying, well, we remember these things, we remember these things, we remember these things. So let's just say that there's a mechanism for this, mechanism for that, and then a mechanism for the other one. So we need to take a look at how are these actually structured. That is, how are they represented? What is that level 2 of Mars tri-level hypothesis representation for these? And that's what's required to show that these are actually different things, not just blue memory and spider memory. All right, so we're going to take a look briefly at some of these models. It's not going to be the focus of today, but just to kind of show you the type of work that can be done. So this is Badley's working memory model. So Badley focused on just the working memory aspect, and he proposed that this is the structure that underlies your working memory. This is how your working memory performs that manipulation of information for complex tasks. So you have this central executive that kind of calls the shots. You have a visual spatial sketch pad. This is where you can remember visual things. So if you take a mental snapshot of somebody, that is, or of something, that is stored in your working memory in your visual spatial sketch pad. These little arrows here mean that you can refresh your memory. So you can kind of focus on what you just saw. You can kind of focus on what you're trying to remember, and it refreshes your working memory. The phonological store, this is where you remember auditory information. So this is where if you were introduced to somebody at a party, and they said, oh, hi, my name is George, this is where George would go into, and this procedure here would be where you're walking around, and to yourself, you're going, George, 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 George. It was George, his name's George. George, George, George. So then when you finally see him, you can go, hey, cheat. Because you know what's going to happen. Anyway, this is the structure of working memory. This is how it's all kind of underlined. And then the connections between language, between episodic long-term memory, so things that you learned before, that you know before, that you can tie to your working memory. So this is this represents a phenomenon of things that make sense once you kind of understand the underlying principles of it. Anyway, this is Badley's model of working memory. All right, next one we have Cohen with his model. So I believe this is Cohen, and this is one of my favorite pictures of psychologists because that's about as fancy as you can get. So Cohen had the embedded processes model. So this is a different type of structure, so we'll zoom in on this. And in this case, he proposed the idea that your long-term memory and your working memory here, your long-term memory and your working memory, so that's the focus of attention, were actually the same things. So they have the same structure, they're the same memory. However, it's just whether they're activated and focused on that changes them into working memory. So your long-term memory is the same as your working memory. It's just when you're not paying attention to that area of your long-term memory or you're not focused on it, we don't call it working memory. So he proposed that working memory and long-term memory are basically the same thing. They're not two different modes. It's just that when your central executive, when that decision-making process in your mind determines it wants to use certain pieces of information, it'll activate them into activated memory. And then if you're focusing your attention on them, this is what we typically call working memory. And then there's other ways. This is the way that your information gets into your memory. But that's kind of the big difference between his model and other models. This idea that working memory is just focused and attended to long-term memory. And then we have Broadband's modal model of memory. And also I chose this picture because he looks like this, just like the more swag than any other psychologist I've seen in a long time. But he really doesn't look like he cares, right? And he's just like, all right. But anyways, this was his model, his modal model of memory. So here we have all the memory systems. We have what he called secondary memory. This is long-term memory. And this is another thing that's kind of frustrating, is that they will call different aspects of modal memory different things. But that's secondary memory, that's your long-term memory. This is your senses. So this is the input. This is where info gets in. So this right here, right until there, that's perception. And then over here, memory takes over. This S system, that is the sort of trace that perception does. So if anybody has ever, if you've ever had a photo taken of you with flash, and then you can see that flash as you look around for the next few seconds, that's your sensory system. That's a form of memory, right? The flash is no longer there, but you still have that information. So that's the sensory system. The sensory system goes into your P system, and this is your working memory, your short-term memory. And then if you do certain things with the information in your short-term and working memory, then it can go and enter into your long-term memory. And that was a very influential model. That was his idea about how different memory things are structured. So when you do research on this type of memory, one of the ways that you can determine if there's different structures is to see kind of behavioral consequences of different forms of memory. So to see if there's any sort of difference between how some memory acts and other memory acts, to see if they maybe are underlied by different structures. And that's what we're going to take a look at when we look at the suffix effect. So the suffix effect was the CogLab that you were asked to do. So in the suffix effect, in this CogLab, what they're doing is they're taking a look at what's the structure of your short-term / working memory. So they want to know what are the kind of characteristics, the principles that underlie your short-term working memory. So on this trial, what happened was you heard digits 1 to 9 presented in random order, right? Almost like a 9-digit phone number. So 9 digits in random order. And your task was to recall them in the same order in which they were presented. So this is known as serial recall. I have that up there? No, I don't. This is known as serial recall when you have to remember things in order. And it's a certain, it's a certain type of memory that is required. For example, if you're trying to remember a phone number, if somebody says, oh, what's your phone number? You can't just tell them, well, there's a 5 in there, and there's a 7, and there's a 2. You have to go in order. You have to remember that information in order. So that's what they were asking you to do here. The independent variable was what type of suffix did you have to indicate that the 9 numbers were over. So you can think of this as a signal, right? You heard the 9 numbers, and then there was a signal that told you that the 9 numbers had finished, and that it was time to enter in what the 9 numbers were in order. So what was the type of suffix, what was the type of signal? Where it could either be a speech signal, or it could be a non-speech tone. And so that was the type of suffix. We'll go into more detail on that in just a second. And then the other independent variable was the serial position, which was the position of each digit on the list. So in other words, were you better at remembering the first number that you heard? How good were you at remembering the second number that you heard? How good were you at remembering the fifth number that you heard? And what about that last number? What about that ninth number? How good were you at remembering that particular number? And in terms of the type of suffix, you either got non-speech, which was a tone, or you got speech, which in this case was the number 0. And it's very important to remember that the number 0 was never one of the numbers that you were supposed to remember, right? So the instruction said you get numbers 1 through 9. So 0 shouldn't have been distracting. 0 should have just been a signal where you were like, oh, okay, I heard 0. I guess the 9 numbers have been presented, and it's time for me to recall. So the setup was like this. If you're like me and you keep your computer muted, and you didn't read the instructions carefully, you might have been staring at this for a while before you realized, oh, okay, it's an audio one. So anyways, you would hear something, and then you would just click on the numbers in order, and then you would hit the next trial, and yeah, it will let you know when you're ready for the next trial. Importantly though, once you heard all 9 numbers, you either heard a tone, like a beep, or you heard the number 0. So it would be like 9, 4, 8, 7, 8, 6, 5, it's hard to just off the cuff. 4, 7, 5, beep, would be one trial. 2, 8, 4, 6, 4, 3, 7, 2, 0 would be another trial. All right. So results for the non-speech condition. This is where the signal to recall the item was a tone. It was a beep. So what did we find? So we have serial position here. So this is what order, in what position was each number that you were trying to recall. So was it the first number? Was it the second number? The third number that you were trying to recall? Was it the 8th number? Was it the 9th number that you were looking for? And then here was the proportion correct, right? So the higher you go, the better your memory. And then if it was all the way up to 1.0, that would be perfect. You remembered it every single time. So what did we find? Well, that is our memory curve. So what we found was that for the first number that you were trying to recall, for the first number in that 9-digit sequence, we were really good at remembering that first number. And then the second number, we were a little bit worse, but still pretty good at remembering that second number. And still pretty good at remembering that third number. But as we go further into the list, we're not so good at the 4th, getting worse at the 5th, really bad at the 6th and the 7th, a little bit better at the 8th, and then it shoots back up on the 9th. It shoots back up on that last number that you were presented with. Then you hear the beep, right? And that was the list that you were trying to remember. So that's what is known as a serial position curve. And this serial position curve is very typical of what happens when you're trying to remember things in a row. It's very typical of what happens when you have to remember the order of things. And it's so typical that they've identified 2 specific areas where you're good at remembering things. First one over here is the primacy effect. So the fact that you are better at remembering the first few numbers is labeled the primacy effect. And then we have the fact that you're good at the last little bit, and that's known as the recency effect. So given your own experience, does anybody have any ideas why we have a primacy effect? Does anybody have a strategy that they were doing? Yep.
You usually spend more time going over the ones from the beginning. So it'll be like apple, orange, banana, and you just repeat it as you hear them.
Exactly. So what has been hypothesized in the best explanation for the primacy effect is that this is that rehearsal. This is that, if you remember in Badley's model of working memory, that phonetic section where it had the arrow where you could continually refresh. This is where you get introduced to George, and you're like George, 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 George. So if the first number was 8. As soon as you heard 8, you probably in your head were sitting there going 8, 8, 8, 8, 8. And then when you hear the next one, 5, you were probably going in your head 8, 5, 8, 5, 8, 5. And then when you hear the next one, 3, you're probably going 8, 5, 3, 8, 5, 3, 8, 5, 3. And notice that as more numbers pile up, you can't rehearse them as much. You can't rehearse them as quickly. Because it's easy to go 8, 8, 8, 8, 8, 8, 8, 8, and get like 20 rehearsals in. But then when it's 8, 5, you're like 8, 5, 8, 5, 8, you have to slow down. And then it also overloads your working memory. Turns out we can only keep about 7 things in our working memory before we start forgetting things. And you'll notice that right about 7 here is where we get to be the worst. So the primacy effect is basically us trying to rehearse that information. What about the recency effect? What about the fact that we are really good at that last number? Kind of good at the second last number. We're really good at the last number. So what might be going on there?
It's the last one that you hear.
It's the last one you hear. It's the most recent one. It's the most recent example. So you might have, and there's also kind of evidence that you also rehearsed that one a little bit, because at this point you've probably forgotten these. So you probably were something like 8, 8, 8, 8, 8, 8, 5, 8, 5, 8, 5, 8, 5, 2, 8, 5, 2, 8, 5, 2, 8, 5, 2, 1, 8, 5, 2, 1, 8, 5, forget it, 7, 7, 8, 5, 2, something else, 7, right? You can do that because it's the last one. And then you hear the beep and you get this recency effect. All right, so this is the data for the beep, and this is your very typical, very classic serial position curve where we have primacy at the beginning effect and the recency effect at the end. All right, for the speech condition. In the speech condition, your signal to recall the item was a 0. And it's important to remember that you were in no ways thinking that you needed to remember the 0. You were in no ways fooled that you were trying to remember the 0. You were told explicitly, numbers 1 through 9. On the screen, there was only numbers 1 through 9. So that 0 should have been a signal that your trial is at an end. Should have been a signal that you are now ready to start to recall. Importantly, you should have been able to ignore it, right? If somebody tells you that, it's kind of like if you're trying to talk to somebody in code, right? If you're trying to tell somebody, oh look, if I scratch my nose like this, it means that I want you to come over and save me from this conversation that I'm having. All right, let's say that you're doing that, and then you scratch your nose like this. Your partner should know that your nose is not itchy. It should know that that's a signal. They should know that that's a signal to do something else. So the 0, you know that that's a signal. You shouldn't try to remember the 0. And you probably did not try to remember the 0. Did anybody here try to remember the 0? Add it into your strategy for remembering numbers?
No, but it slipped in there anyway.
It did slip in there. No, you're right. And that's the point of this CogLab here. So nobody tried to. Nobody wanted to do it. But if you take a look at the classic serial positioning curve when there was a tone, if we now take a look at what happened when we added the 0 as your signal, even though consciously you knew you could ignore it, even though consciously you knew that's not one of the numbers that I should try to remember, it affected your curve. And that is your serial position curve now for when you have the suffix effect. And very interestingly, you can see that there is still that still that primacy effect. You still have a little bit of a recency effect right there. But importantly, you have that gap right there. Your last number has gone down in accuracy. So that 0 has messed up how well that you remember your last number. And that difference is known as the suffix effect. And a clue to what's going on, and we had a suggestion already made, is that that 0 is making its way into your working memory. It's making its way into your memory system. Even though you don't want it to, it's still getting in somehow. And there's evidence here that it is getting in. So does anybody know what 2 points on that graph really indicate that even though you tried not to, the 0 worked its way into your working memory and forced another number out? Mm-hmm. Yeah, exactly. So if you take a look, it's hard to see from the side, it's 9 and 8. So if you take a look during the suffix effect, how well you did on your last number that you were supposed to remember, not your actual last number. Remember, 0 was your last number. But how well did you do on your last number that you were supposed to remember? You do about as well as the second last number when you got the beep. So the fact that you do about as well as the second last number when there is a beep indicates or highly suggests that in your mind you had this number as your last number, right? You came to the end of the list and you had that number in that final slot, and then you heard the 0, and even though you knew you weren't supposed to remember the 0, it popped into your memory. It pushed its way in, pushing this last number, which should be up there, down to the second last slot. So it's very strong evidence that that's what's happening. The fact that these two are so close in their recall percentages. All right, so that is an indication of the structure of your working memory. How does it work? What gets in? What doesn't get in? And that is, once again, we've already talked about this. So, what modal memory system? Oh, we didn't go specifically in this one. So, what modal memory system is causing the primacy effect? What is the modal memory, short-term memory, working memory, long-term memory, that is causing the primacy effect? The fact that you can remember those first three for a longer time than the other ones. So what do you think might be that modal memory? It might differ depending on the strategy that you use. Mm-hmm. So one possibility is working memory, in that you keep refreshing the numbers in your primacy, the numbers that you first heard, they've occupied places in your working memory. You keep refreshing them to keep them alive, and there's just no room for any of these other ones down here. The other possibility, though, has to do with, so that's one possibility. The other possibility has to do with rehearsal. And rehearsal is one of the ways of taking something from your working memory, your short-term memory, and putting it into your long-term memory. So it's quite possible that by doing things over and over and over again, you just made it go from your working memory to your long-term memory, where you could store more information for a longer period of time. Because remember, you heard these first, so to remember them, you had to hold on to that all the way until you heard that beep, and only then could you start recalling those. And that idea of rehearsal is, it's, just to be clear, an ineffective way to get something from your working memory into your long-term memory. And that's the idea of, if you're studying, for example, you'll study something, then you'll study it again, then you'll study it again, then you'll study it again. And it does work, but as you read in that chapter 7 kind of teaser section on the first exam, there's better ways to get stuff from your working into your long-term memory. All right, so what modal memory system causes the recency effect? So what modal memory system might cause that last item to still be recalled at a very high rate? I'll kind of give you a clue. As soon as the beep occurs, you can start recalling this information. So it does not take a long time between the beep and between when you have to recall that information. So you only have to recall it for a short term. There it is. Okay, so that one is probably underlied by your short-term memory system. So it's not necessarily that you're working with that number. It's not necessarily that it's in your working memory and you're keeping it alive. It's just that it's the last thing that you heard. It's still in your short-term memory. Your short-term memory remembers things for a short period of time. So whatever number this was, it's gone. It decayed. It stayed in your short-term memory, but it died out. But this one here, it's still alive. And if you can enter in those numbers before it dies out, you can still remember what it was that last number was. All right, and memory phenomenon was reduced by the suffix effect. We kind of took a look at that. It was the recency effect. So very interestingly, there we go. The decrease in the suffix effect only occurs in the recency portion. Has virtually no effect in the primacy portion. So the first three numbers, still very highly recalled, really only affects that recency portion of the curve. And that again is because that last number works its way either into working memory or into short-term memory. That 0, even though you don't want it to, pops in to your working memory. All right, and then what modal memory system was affected by the suffix effect? We already mentioned this. It seems to be your working memory and your short-term memory. So for this, let's see where I was going with this. All right, we've already addressed a lot of these. I think we've kind of preempted the discussion. But one of these things, what does this tell us about coding in long-term versus short-term working memory? What does this suffix effect tell us about how things are coded? What might be the different types of underlying structure for long-term memory versus short-term memory? Or working memory? Well, let me give you a hint. What kind of information can make it into working memory? Or do you have control over what type of information makes it into working memory? Let me back up to that graph a little bit right here. So, if you had control over what goes into working memory, would you see the suffix effect? No, you would not. If you could ignore the 0, if you could code that 0 as a signal, if you could code it as something that you could ignore, we wouldn't have this suffix effect. All right, so this is the same kind of thing where if you're trying to remember, the directions somewhere. If somebody tells, if you're asking for directions, all of these examples presuppose your phone died. So your phone died, and you have to ask for directions how to get somewhere. And somebody comes to you and says, all right, I know exactly how you get there. You go down 2 streets, you take a right, then you walk for 2 blocks, you take a left, and then you're going to go down another 3 blocks, take another left for 1 block, and then go down 2 blocks, and you're going to be at your destination. The thing you're going to start doing, and I already forgot what the directions were, but the thing you're going to start doing is you're going to start saying, all right, 2 blocks, turn a right, 3 blocks, turn left, another 2 blocks, there's your destination. 2 blocks, turn right, 3 blocks, turn left, another 2 blocks, there's your destination. And you could try to ignore that annoying friend of yours that is just sitting there going 4 blocks, 2 blocks, turn right. You could say to yourself consciously, I'm ignoring that person. And what's coming out of their mouth, I am not going to process. And as we've seen here, you can't. There's a reason that's annoying, because you cannot filter it. You cannot say, I'm not going to pay attention to that. And as soon as they say 4 blocks, because you're trying to remember that type of information, it works its way in and it throws off your directions. Yep.
So it wouldn't have an effect if it didn't follow like the pattern of the information. Like if they just said banana instead of 0, would it still have an effect?
They've done studies on that where they've tried to see exactly how it would categorize it. If I remember correctly, bananas would not have an effect. They did studies where they've tried a bunch of combinations. I seem to remember one where they had sheep noises versus like some other type of noise, just to make sure whether it's actual like live noises versus just computer beeps that might be doing it. But that is, without being able to tell you exactly, that's the kind of question that you would ask, that's the kind of work that you would do. Because if it was that bananas had no effect, then that means your working memory, at the very least, can tell the difference between numbers and words, right? It can, at the very least, it codes at that level, and it codes the fact that these are numbers and these are words. If bananas still affected the, the semantic memory, the working memory, if you still had the suffix effect, that would mean that we code in a more general term. So then you could say, well, maybe it's human language that we code, right? We're just going to listen to human language. And that's when you take sheep noises as a signal versus, somebody saying, bananas. Maybe we code our own language. So you could have somebody saying, bananas versus somebody in French, saying bananas, right? So that's all the kind of, research that they would do to try to figure out what is it that your working memory is coding. But at the very least, it's not very conscious. It's not very able to be controlled by you, unlike your long-term memory. So your long-term memory seems to be something that is consciously controlled. So all of you have become very practiced at consciously controlling your long-term memory. Every single time you say something like, I need to learn this for an exam, basically what you're saying is, I'm going to put this into my long-term memory. I'm going to make an effort. This is going in, and I have control over it. Anytime you've probably been successful at this too. You've probably heard some information and said to yourself, I don't care to remember that at all. I'm not going to ever use that. It's gone. And it is, right? And later on, you can't even remember what somebody might have said. So your long-term memory seems to be different than your short-term memory, in the fact that you can control what goes into your long-term, but you can't really control what goes into your short-term working memory. So you can ignore the zero which in long-term, but you really can't ignore it in that working short-term memory. And that's a good indication that they actually are two different types of memory, right? It's not just that some things are remembered short-term, some things are remembered long-term. It seems that there actually are underlied by different structures. One of them cannot filter out information depending upon how that information is coded. Long-term memory you can filter out, and you can choose what goes in there. All right, so any questions on that before we move on to the next topic? Okay, so the next thing we're going to introduce, speaking of long-term memory, they've also identified different types of long-term memory. So we have this vast memory storage mechanism where we can remember tons of things, but we can also remember different types of those things. Yep.
Sorry, so how does like attention play into that? That's what we were just looking at. So like, let's say, I guess we were told to be attentive towards, not necessarily, but I guess the question is like, how can we differentiate things that are filtered out by our attention versus this sort of thing, the suffix effect?
Oh, okay. Well, one of the arguments, for that would be that this is an indication of that you're attending to that information. So if you remember, in order to process information, you have to be attending to it at some form. So in order to do anything in memory, you can make the argument that you need to attend to it in order for it to be in your memory. What this would say is that your attention cannot be focused so narrowly that you basically attend by category. That would be one of the implications of this. So you can attend to numbers, but you can't attend to specific numbers. So if you're attending to numbers, then of course 0 is going to make its way in because you're attending to that category. 0 is part of that category. If you're able to attend to specific numbers, like 1 through 9, then 0 wouldn't find its way in. And it might be that the 1 through 9 could not be attended to specifically because it was too long. So it could have been that if they said, well, just attend to the numbers 1 and 2. Like your only job is to determine, was the order 1 and 2, or was the order 2 and 1? In that case, maybe the 0 would have no effect, right? Because you can focus your attention on that. So it's attention in a lot of these models is the way that it gets in to memory in the first place, that you need to attend it, and that's what you do in processing. So another way of thinking of that is, if it's in your working memory, you're attending to it. So if you're manipulating it, then you're literally processing it, and that's what attention was at its basic, that processing of information. All right, so long-term memory, different types of long-term memory. So we have a few different types, a few different kind of ways that they'll split up long-term memory. We're going to start off with explicit versus implicit memory. So explicit memory, these are memories that are used with awareness. These are memories that you are explicitly aware of, that you know you're aware of, that you can use the same terms. You're aware that you know these things. So explicit memory, memories that you use within awareness. So this includes subsets of explicit memory, things like episodic memory. So episodic memory is memory for things that happen to you. Like hitting your head on a screen. That's something that you'll remember later. That's something that actually happened to you. When I asked that example about your best Christmas ever, right? That's an episodic memory. If I asked you, where did you go to school in elementary school? Have you seen a particular movie? All of these things that happen to you, your life story is basically your episodic memory. We also have semantic memory. And this is the memory of things that you know about. These are the facts that you know. This is the information that you know, that you don't necessarily know where you learned it, but you know that you learned it. So if you know that George Washington was the first president of the United States, that's semantic memory. That's information that you have stored in long-term memory. If you remember that your grade 2 history teacher, Mrs. Hinkle, taught you that, that's an episodic memory, right? So episodic is for things that happen to you. Semantic is for just kind of general information, things that you know. So in this class, you are hopefully loading up your semantic memory with cognitive psychology phenomenon and terms and concepts. And later down the road, if you remember, I remember Dr. Yadichevich told us that one time. He gave us that example of Spider-Woman to explain memory. That would be an episodic memory, memories from yourself. But importantly, these are two subsets of explicit memory. You're aware that you know these things, right? You're aware of these things and you're conscious of it, and you can explicitly state them. So if somebody told you, do you know who the first president of the United States was? You can say, yes, I do, and I can tell you it's George Washington. I can be explicit about that. You can contrast that with implicit memory. And implicit memory are memories that you have, that your behavior says that you have, indicates that you have, but you're not aware of them. And this includes memories like procedural memory. So procedural memory, if you have memories on how to do things, and that's indicated by your behavior, you have this procedural memory, but you might not be aware of what it is that you remember, right? You might not be aware of what it is that you're doing. So for example, one procedural memory that we all have is the memory for how to walk, right? That's a procedural memory. So we all have this ability to walk, and we know that you remember how to walk, because if somebody said, can you get up and walk, nobody ever has been like, I forgot how to walk, right? But you can't explain it, right? It's very difficult to explain. So let me just go have that example. Where'd you go? There it is. So it's very difficult to explain how it is that you walk, because it's implicit memory. You don't know. And this was shown, if you ever take a look at how well we walk, that's our implicit memory for walking. If you then take a look at how well robots walk, that's explicit memory for walking. And it was nowhere near how good it is that we walk. So this kind of idea of implicit memory, memories used without awareness, how do you walk, how do you throw a ball? Have you ever tried to explain to somebody how to throw a ball? It's like you you throw it, right? We don't know what the steps are in order to throw a ball. Priming is the memory where if you think of one thing, you think of another. So if I say Batman, you probably think, you should all be saying Robin. It's weird, he hasn't, okay, I'll give you a pass on that one because he hasn't shown up in the movies very much. But if I say Harley Quinn, you say Joker, because they go together, because they've been paired together. So you have a memory for that. You have a memory that Harley Quinn goes with Joker. You might not be aware that you have that memory, but it's shown in priming. It's shown in that procedural kind of, memory without awareness. And then conditioning is oftentimes shown in memory for emotions. So if you have a phobia, or if you're afraid of certain things, you might not remember why you're afraid of it. So if you have a fear of spiders, you might not remember a traumatic incident that you had with the spider, but your emotions show that you have an implicit memory for it. You're not aware why you're scared of spiders, but you just remember that you are. You're not aware why you're afraid of clowns, but you just remember that you are, right? Or you might, it goes the opposite way too. You might not remember why you have positive feelings towards something, but your body remembers that you do, and that's actually the basis for advertising. Advertising is using commercials, using repetitive presentations of something, of fun scenes with a product, so that when you go to the store and you see that product, your implicit memory, through conditioning, evokes those positive feelings. And when you're looking at all the products that you could buy, you're like, well, I don't really know about this one, I don't feel good about this one, but this one over here, for some reason, I feel good about it. I think I'm going to grab myself a Diet Coke. All right. So those are the different types of long-term memory. We got implicit versus explicit. Implicit memory that you use without awareness. Explicit memory that you are very conscious of, that you are aware that you are using. And we're going to take a look at how we can test to see what do we have, what do we know that's implicit, what do we know that's explicit in this implicit learning CogLab. So on each of these trials, a dot was going to appear in one of 4 locations. And your task was to press a key on your keyboard as quickly as you can to indicate the dot's location. So as soon as the dot popped up, each of the 4 locations had a different key that you would press, and you were supposed to press as quickly as you can and as accurately as you could where the dot appeared. So the independent variable was that there was actually 2 presentation conditions that you could have found yourself in. And these are either or. So half of you ended up in the random condition, and then the other half of you ended up in the pattern condition. And in the random condition, the location was completely randomized. It never followed a pattern. In the pattern condition, the location of the dots followed a pattern. And this pattern repeated over and over and over again, except on block 5, and we'll take a look at block 5. So it reverted to random for block 5, but other than that, it followed that pattern. So you would have a display like this. So we have far left, we have right, we have far right, and then we have left. And as quickly as you could, you would have to indicate where that dot was by pressing the corresponding, if you can do it with a mouse, but they also had the keyboard shortcuts in order to do that. And those keyboard shortcuts were right here. So if it appears in the leftmost location, you press Z. If it appears in the second location, press X. Third location, you press the dot. And rightmost location, you press the backslash. So those were the rules. And you were trying to do this as quickly as you could. So what are the results? What were the results for the random condition? So in the random condition, once again, here we have blocks. So you would do this multiple times within each block, and then they just basically took your accuracy and calculated it for each block of trials, and took your reaction time. And your reaction time here is in milliseconds. So how long did it take you to press when each location popped up? And we have it was pretty quick. This is half a second down here, and it goes up to about 2/3 of a second at the top there. So how fast were we at indicating where the location was? Well, we were that fast. All right, so this is for the random condition. Could occur anywhere. And as you can see in that first block, you weren't doing very well, right? So in that first block, it took you a while to find the location. It took you a while to be like, okay, that's far right, Z, that's in the middle, you know, I'm pressing X. But then you got way better. You got way better by the end. And that is an example of explicit and implicit learning. So that curve there is caused by a combination of implicit and explicit learning. So implicitly, what is the type of learning that might be occurring? Or explicitly, what is the type of learning that might be occurring? Any suggestions on that? Well, let me ask this. You have an idea? Yeah. You get used to what you're doing. Exactly. Is that?
Yeah, well, I was gonna say that you get more used to like the keys and start understanding.
Okay. So that get used to what you're doing. That is very indicative of implicit learning. So it's not that you memorize the keys. It's not that you memorize the rules. It's that you got used to what you were doing. And that getting used to, because you can't, if I was to ask you, well, how did you get used to it? All you can really say is, well, we did it over and over again, right? But if I ask you, well, what's the kind of strategy that you use to get used to it? You couldn't answer that. It's an implicit memory. It's a procedural memory. So part of this curve, part of the reason that you got better is because you actually got better at pressing the numbers, right? Or, sorry, at pressing the keys. Kind of like when you go into a grocery store and you see the cashiers that have been working there forever and they're just like, you know, super fast. You got used to it. It could also be explicit learning, because it could be that in the beginning you had to think about it a little bit. You had to sit there and go, okay, wait, far left. What was far left? All right, it was Z. I'm going to press that. And I'm aware that Z was for far left. And I'm aware that slash was for far right. But you have to think about it a little bit at the beginning. That would be explicit learning. So as you got better at the rules and you were more quick at remembering what the rules were, that could decrease your reaction time through explicit learning. As you just kind of got that motor memory, that muscle memory for where you got to press the buttons, that could increase it through implicit learning. All right, so two possibilities for, or two combinations, could be both and, for why this reaction time decreased, why you got faster. But now let's take a look at the pattern condition. So this is the random condition here. And if we take a look at the pattern condition, we can see that people were faster in the pattern condition. So you were actually quicker in the pattern condition. And that can only be explained by implicit learning. And I will prove that right now. Who here knows that they were in the pattern condition? Half of you were in the pattern condition. So hands up if you were in the pattern condition. All right, exactly. You're right. None of you should put your hands up. Because most people don't detect the pattern. And yet, you did detect pattern. Because people in the pattern condition were faster. This is an indication that you detected the pattern. And the fact that you don't know that you were in the pattern condition means that it's not a part of your explicit memory. If it was part of your explicit memory, you would have been aware. If it was part of your explicit memory, you would be able to say, oh yeah, I noticed this, I'm aware of this pattern, I was in the pattern condition. So the fact that nobody mentioned that they were in the pattern condition means that this difference here, right, that difference between these conditions, that difference can only be because of implicit learning. The only difference between these two is the pattern. Nobody noticed that they were in the pattern. That excludes explicit learning. So the only thing that it could include is implicit learning. And if we zoom in on that, you can actually see here that in block 5, where both conditions were in the random condition, you can see that both conditions are about the same speed. right? There's a little bit of a difference there, but it's not significant. But in the condition 4, where this is a pattern and this is random, and in condition 6, where this is this is a pattern and this is random, you see those differences. That can only be explained by implicit learning. So no difference there, big difference on the other two. And that's why they kind of throw in that block 5, just to make sure that the people in the pattern condition are just not a sample of grocery cashiers that are just really, really good at this. All right, so why was the performance better in the pattern condition than in the random condition? We touched on this. It's implicit learning. The only thing that could explain this, the only difference is that you were able to learn the pattern. You weren't aware that you learned the pattern, but it did affect your behavior, and that was implicit learning. This was my backup question in case anybody suspected that they were in the pattern condition. So I'm not even going to ask. Probably nobody noticed that they were in the pattern condition, which probably means that you did not notice what the pattern was. In the pattern condition, this is what the pattern was. And through repeated practice, you were able to learn this pattern. Even though you didn't know what the pattern was, your unconscious memory processes, your procedural memory, was able to learn it so that you could react faster. You could anticipate that after right, far right, far left, then was a left, then a far right, right, left, far right, far left, and then you repeated the whole thing. You actually were able to detect this pattern, and that's why you were faster. So the fact that nobody ever guesses this, again, is very strong evidence that you were explicitly unaware of this. You had no explicit memory for this, but it affected your behavior. It affected your reaction times, which means that you were implicitly aware. You had that, I shouldn't say implicitly aware. You had implicit memory for that pattern. Yep.
Well, I'm pretty sure that I was in the pattern group, but only because there's that small chunk in the middle,
Mm-hmm.
The far left, far right, like just those,
Yep.
the middle 4.
Oh, okay.
I recognized that pattern, but not the whole thing, but it felt, I know I saw that little chunk multiple times.
Okay. So were you able to, were you aware of that? Like, I know you were aware that something was repeating. Did you know that, oh, it's these 4 keys?
Yeah, but
Okay.
I play the piano, and I also, so I thought about it in those terms, like I thought about it as notes, really,
Mm-hmm.
and associated that with, but yeah, I definitely noticed that, just that middle section, not the whole thing. But the
Okay. So in that case, part of your decrease in reaction time, part of your faster performance, would have actually been due to explicit memory.
Mm-hmm.
Because if you're aware of it, then it's possible that some explicit memory was the cause of it. If you're unaware of the rest of them, though, that would have been an implicit portion of it. Mm-hmm.
Mine said I was in the random condition, but I could have sworn it felt like there was a pattern in random times.
At the beginning or at the end of yours, you were told?
At the end, it tells you.
Oh, okay.
When you read it,
Yeah?
it tells you what pattern you're in.
Oh, okay, I was unaware.
Yeah.
So that's actually interesting that you would mention that, because I don't think CogLabs would try to fool you or
Right.
lie to you during the
I don't know if it
debriefing.
was just because it was so long and so many trials it started to feel like it. Maybe.
There is we encountered this before when we were looking at face perception. There's this phenomenon called Peridolia, and it is a phenomenon where we try to impose order on the world. Our minds are just made to impose order. And that detecting of a pattern when patterns aren't there is just something our minds just do that. It's something that we do. And that is one of the reasons why racism oftentimes occurs, and that's why representation in media is so incredibly important, because our minds will pick up patterns and try to pick up patterns even when they don't actually exist, because that's just how our minds work. This is also why conspiracy theories are so kind of tempting and seductive, because random things happen in the world, but our minds just want to impose that order. And it's better for us to think that there's some conspiracy that is causing certain things, our minds just work that way. We're more apt to say, yes, there's a pattern there. There has to be. And when somebody suggests a pattern, like, oh, you know, the Earth is flat and it's big science that's trying to cover it up, because if the people knew, I don't know, nothing, right? Like, what would happen? Really? Why are we keeping this a secret? But we try to impose that order on our thing. So if any of you were in the random condition and you thought, no, there was a pattern, it's that processing, it's that natural tendency of our mind to see things where there might not be patterns. Yeah.
Like trying to make sense of something that's not, like it was all random, but I guess just doing it for so long, I thought I
Yeah.
a pattern.
Yeah, there was actually, we'll end with this example. There's this Michael Keaton movie. I know it's a Michael Keaton movie. It's a horror movie. I don't recommend it, but it's, I think it was called White Noise. And it was about, there's people who listen to white noise. They listen to like static on a TV or static on a radio. And they believe that spirits can communicate through white noise. And they will literally listen to things. And every once in a while, just because of like the way that your mind works, random noises will come together and you'll hear something like Helen. And they'll be like, oh my gosh, like Helen must have died here or something. And it's just, you show it to somebody else and you can't do that, either. So I'll give you one last example. This is a sort of, this is going to be a sort of teaser trailer for when we get into language. You try to impose order on language sounds as well. So the sound waves that come into your ear, they're very, like if you ever take a look at them, they're very complicated. Your brain imposes order on them, and as it turns out, different people's brains will incorporate or impose different types of order, and that's why that Yanny versus, what was the other word I forgot? Laurel. That's why the Yanny versus Laurel thing blew up, because half the people heard Yanny, half the people heard Laurel. It's the same kind of pattern, but one person's mind imposed a certain type of order on it, another person's mind imposed a second type of order, and when we get to language processing, we'll see exactly what was going on. All right, so I think that is good for today. So next class, as I mentioned, exam. That's all we're doing in next class. So come here ready to do the exam, same as last time in class. Only thing we're doing, multiple choice, bring your pencils and erasers. And other than that, we're done for today.